Okay. So the models that we talked about in the previous lecture were all static models, and I'm now going to infuse them with a temporal dimension. And in particular, our analyst, our econometrician was interested what the agent chose and with what probabilities. Now we're also going to be interested in how long the decision takes. And we're going to take that temporal dimension seriously. We're going to try to maybe make some inferences from that response time. So sort of intuitively, our agent now is facing this decision problem where if the menu is left and right, at each instant they can either choose between left and right, or they can delay the choice. And then at the next instant, again, they can choose between left and right and then stop forever, or delay the choice again. Why would they delay? The answer is that they're going to delay their choice because they can get more information if they wait more time. So either there are some signals coming at them from the screen, and they're just going to be able to spend more time processing these signals. Or maybe they're going to be sampling their memory or their introspection about, these items that they're facing. Maybe they have some experience with these items. They're trying to recollect that experience, and the longer they'll think about this, the more information they will have. So these are the benefits of delaying choice. There are also costs, obviously, of spending more time on one particular task, because that time could be spent on other tasks. Maybe it can be done with the experiment earlier and go home and play a video game. Or in real life, maybe if you make the choice earlier, you enjoy the fruit of that choice earlier. You get to consume earlier. And so because there are these two sides of delaying, benefits and costs, there are also going to be two effects that are going to be very interesting. The first one is sort of a purely informational effect, that spending more time on a task will give the agent more information, and therefore it's going to lead to better decisions, and more informed decisions, because the agent is going to have a better sense of what the true state of the world is, and they're going to be able to tailor their action to the state better. So if we force the agent to stop at time t, we would expect the agent to make better choices if we force them to stop later rather than earlier. And so the accuracy of the choice we would expect to be increasing in t. This is often called the speed accuracy trade-off. The agent is facing a speed accuracy trade-off. They can either make fast decisions or good decisions if they make them slowly. So that's sort of pretty obvious. The less obvious effect is coming from the fact that the agent gets to choose when to stop. And so, because time is costly, the decision whether to continue or stop will depend on how much the agent is expecting to learn if they continue. And so in particular, if the agent gets a pretty good signal, a convincing, informative signal, they don't expect to learn much more, they will stop. But if they get a noisy signal, they will probably continue. And so you see that intuitively, if you get a informative signal early, you're going to stop. And because the signal was informative, you're going to make good decisions. You're going to make informed decisions. If you get a noisy signal, you're presumably going to make worse decisions if they are guided by noise. And those are going to be decisions that take more time, because on those paths you will want to explore the problem more. So this dynamic effect can reverse this equation and basically intuitively, the rest of the talk is gonna be formalizing this intuition. Intuitively, you'd expect that if the agent is freely allowed to choose when to stop, early choices will be the choices where the agent gets a good signal and makes a good decision. Late choices is going to be the situations in which the agent is kind of a little bit lost, wants to explore more, and maybe makes a worse choice. And there's going to be a balance between there's going to be these are pushing in opposite directions. So the from this alone, it's not clear what's going to happen. Yeah. It's not assumed. So they may get an informative signal later, but they may also get a noisy signal. No, this is just a very intuitive argument. But at least they make, when they stop early, that's a sign that they had an informative signal. Eric?
In the experiments Mike was talking about yesterday, it appears that the second effect was stronger than the first. So people were making more errors, even though they were delaying the response time. Was coming going to?
Yes, the second effect eventually will win. So that's the stylized fact in, at least in the perception literature, is that, if we look at the agent solving the same problem over and over again, like we did before, but now we group their decisions by bins. When did they stop? The early decisions are better than the late decisions. So that's true in perceptual choices, very well established. It's also appears to be true in some economic choices, although that's more tenuous.
Just the benchmark. If time is not costly, there shouldn't be a difference. Right?
If time is not costly, they should never make a decision.
Assume that they want to get within epsilon,
they will all wait. Yeah.
So it's the cost of time.
It's the cost of time. Now, just a small comment. This sort of goes against the sort of popular intuition in like books like Kahneman, Thinking Fast and Slow, where fast decisions are bad. But those are sort of experiments which are kind of trick experiments. They're especially designed by smart psychologists, where there's like a trick question where you think you have the right answer, but that's actually it's the wrong answer. And so on those trick questions, people get fooled a lot. But I'm not going to talk about trick questions today. Yeah.
It might be worth mentioning. Ariel Rubinstein has.
Yeah, he's going to be talking about trick questions, presumably. We'll see. We'll see. So we'll see tomorrow. Yeah. So Ariel also contributed to this kind of experiment. Okay, so I want to have a model of all of this, so that this was just an intuition, but this this is economic theory. We want our intuitions to be guided by principles. So let's do it. What are the observables? What can the analyst see? So there's some state space, maybe the true weight of each item. That's the true state. Time is either discrete or continuous. I will, as much as possible, try to make everything discrete because it's easier. But some of the models are cast in continuous time, so I'll mention that. This literature typically studies choices from binary menus, so there's going to be left item and a right item. And the analyst now observes for each state a probability distribution over the menu and time. Joint distribution. So how long the agent thought and what they chose. I'm going to record this for many choices. Hopefully these empirical frequencies will converge to this theoretical probability. And that's what I'm going to take as given. So some examples in the character recognition example from the first lecture, the menu is these two characters. These are the possible answers that the subject in the experiment can give. The true states is what is the true character that was presented to the agent. The analyst knows the true character and runs this experiment many times. And rho S of CT is the probability that the agent decides for exactly t seconds and chooses C if the true character was S, so either S, either C or E. In the weight discrimination example, the menu is the left item, the right item. The true state now is a pair of numbers, the weight of each item. So the state space is continuous, and the analyst knows the true weight of each item and runs this experiment and determines, what's the frequency of responses and time and times. Make sense? Okay. So what's the model? It's going to be sort of a dynamic version of the model that I sketched out before, the Bayesian expected utility model. So now at each time, the agent receives. Oh, question? They can delay. This is the yes, but ultimately they will have to choose either left or right, and so by choosing delay, they just increase the counter on t. Basically, that's how you can think about it. Okay, so for each, they receive a message in each time period. There's an additional incremental piece of information. And so superscript t is going to denote the history of these messages up to time t. As before, the agent has a prior and a deterministic utility. Maybe they get rewarded by when they guess the correct character. So if we force the agent to choose at time t, their choice would maximize their posterior expected utility conditional on their message. So that's exactly the Bayesian expected utility model from the first lecture at each point in time. But now the twist is that they don't have to choose at time t. They can delay and get another signal at a cost. So when are they going to stop? What's that going to look like? The key idea, intuitively in the model, is that the decision whether to stop or not can depend only on what are the messages that the agent received so far. They can't see the future messages. No prophets. Yeah. So to model this a little bit more formally, it's useful to think of a big state space. Omega is the Cartesian product of the true state and all the possible messages. The probability distribution of our omega is sort of the joint given the prior on the state and these conditionals over messages, these what was called betas before. For each omega, m superscript t of omega just denotes the messages up to time t in that state. And the agent has what's called a stopping region, sigma t, which is a subset of mt. These are the message histories after which they stop. So a stopping time is a random variable. It's a mapping from omega to time, such that for each t, the agent chooses to stop at time t if the cumulative message up to time t belongs to this stopping region, and otherwise they continue.
Presumably we can derive the stopping time costs.
That's what we will do. Yep. This is just a general sort of universe of all stopping times. Each stopping time will look like that, and the agent is going to be choosing between these stopping times. So that's how it looks like in discrete time. In continuous time, you have to use what's called filtrations to define a stopping time. I'm not going to go there. Okay, and yep.
You don't want to have a different stopping region for each of the possible responses. Stopping region when you'll stop and say L, and a different stopping region for when you'll stop and say R.
So this is the union of these two regions. You could break it into two. And in fact, that's what the agent will do. Sometimes they will choose L, sometimes they will choose R. Okay, so what's the optimization problem of the agent? The agent is going to stop optimally, so there's going to be some cost function. Waiting is costly, so this the longer I wait, the more costly it is. And the optimal stopping time, tau star, solves max over tau, over all stopping times, the expected utility of my, so chi t was my optimal choice conditional on stopping at time t. So the expected utility of my optimal choice conditional on stopping at time t minus the cost of stopping at time t. This model was first formulated in statistics. It's known as sequential sampling. So the analyst is a statistician. They can run some experiments at a cost to make better decisions. It was developed during the wartime. They're testing a batch of ammunition. How do you test? You have to explode it, so it's costly. And how many more do you want to do before you declare that batch to be ready to go? Oftentimes, and I'll mostly talk about the case where the cost is linear in time. So each instant of time costs the same. The marginal cost is constant.
Every signal costs C.
Every signal costs C. And there's no discounting. So I mentioned one of the costs of delaying is that you get to consume what you choose later. But in the context of the experiments that we will talk about today, this is not really a concern. All of these payoffs are at the end of the experiment anyway. So you don't get to consume earlier. You just spend either mental energy or your own time on these decisions. There are versions of the model with discounting, but I won't talk about them today. Okay, any questions about this? Okay, so now we just have to solve this model. So we're going to solve a very simple case first. It's called a Wald's model. The cost is linear in time, the menu is binary, and there are two states, left state and the right state, and the payoff is basically you have to match the state, just like in the character recognition task. And conditional on the state, the messages are IID, normal, with the mean delta and variance sigma square. Delta is a function of the state. Okay, so that makes sense. In our static model, the distribution over messages depended on the state. This is how we operationalize it here. This is the functional form. Delta is either positive if the left item is heavier. If the state is L, and is negative if the state is R. So in this model, it's sufficient for the agent to keep track just of the running sum. The order of these messages doesn't matter for the agent. So I'm going to denote this by m bar. It's not an average, even the bar is there. It's just a sum. And what is this m bar? It's a random walk with an unknown drift. The drift is either d or minus d. And that's what the agent is learning about, is what is the drift of this random walk. Okay, so what does the Bayes rule say here? if you apply the Bayes rule here, you know, take the log. So you have to use, you know, what's the density. I'm not going to do the calculation. What's the density of the normal distribution? This all goes into this formula, and the log of the posterior odds is equal to the log of prior odds, priors, plus sort of the signal, the cumulative signal, times some fraction that depends on the noisiness. Okay. So if we force the agent to choose at time t, the agent would pick L, the left item, whenever this likelihood ratio, log likelihood ratio is positive, whenever they think the left item is more likely than the right item. Do you have a question, Sergio? That's a good question. That's a good question. So does that make sense? So just like before, just like in the character recognition task, they just want to match the states. So whenever they think the left state is more likely, they're going to pick L. So if the prior is symmetric, they're going to pick L if and only if this signal is bigger than 0. Because if the prior is symmetric, that means P of SL is equal to P of SR, so that ratio is 1, log of 1 is 0. So there you go. So the agent picks L if the cumulative message is positive. So suppose the state is SL, the agent is going to choose L. What's the probability that the agent is going to choose SL? It's the probability that the cumulative message is positive, which is given by the CDF of the normal distribution, because the cumulative message is normally distributed. So that's the formula for it. The cumulative message has, distribution is normal with mean t times delta and variance t times sigma square. So if you plug it in here, that's what you get, and that thing is increasing in t. So that's just a check on our first intuition that the first sort of informational effect works the way we want here. If we force the agent to decide later, they're going to make a better decision than if we force them to make their decision earlier. Yeah?
Is this equivalent to a drift diffusion model?
We will get there. It is, but we're not there yet. Yeah. So here we're just, at this particular slide, we are just forcing the agent to stop.
So choosing time may make you an impression.
That's what's going to happen on the next slide. But on this slide, we're not letting the agent choose the time. We're just forcing the agent to choose left or right at time t versus t prime. Yep.
Just a question on drift. You was written that it was unknown drift.
Mm-hmm.
So drift is known to be u or minus t.
So that's what's unknown is the sign of the drift.
The sign.
But the magnitude is known. Yeah, that's a very important distinction. We'll get back to this distinction later. Yeah.
So the user is supposed to stop at the first instant t, then n bar of t is 0?
No, the agent is forced to stop at some exogenous time t on this slide. I did something terrible. Control L. It's the only Windows shortcut I know. Okay. So what about the agent is not forced to stop at any particular time? They can choose when to stop. What's going to turn out is that this first effect, the informational effect, is exactly offset by the stopping effect. In the Wald model, accuracy is a constant function of time. So early decisions are as good as late decisions. You'll see why in a couple of slides. So the theorem is that the optimal stopping time for the agent is such that they stop the first time the absolute value of the log likelihood ratio crosses some threshold k that's independent of time. And if the prior is symmetric, you can rewrite this as the agent is going to stop the first time the absolute value of the cumulative signal crosses some other threshold b. So graphically, the kind of the model looks like this. The agent has some threshold b and minus b. Here I take it to be 1. The red thing is a path of this random walk with drift. On this path, it hits the upper boundary, so the agent is going to think that the left item is more likely. They're going to choose the left item, and they're going to think for 0.2 seconds on this path. Different path gets drawn. They're at 0.2 seconds. They're almost convinced they should choose right, but actually not quite enough to make them stop. They continue, and actually they end up choosing left, but it takes them 0.8 seconds. Okay, different path. They end up choosing right. That's the kind of thing that ends up happening. That's what the optimal thing to do is. Any questions? This is under the assumption of IID signals. This actually, yeah. And linear cost. Okay. So this model was brought to the psychology literature in the 60s and the 70s to study perception and memory retrieval. So it's an extensively used model in psychology and neuroscience, cognitive science. Oftentimes, people in those literatures abstract from the optimization problem, and they actually use this boundary hitting sort of model as a reduced form to generate a probability distribution over choices and times. And that's what's called the drift diffusion model. So formally, a stochastic choice function has a DDM representation if there exists a drift and a noise parameter and a boundary such that the cumulative signal is a diffusion. So that model is cast in continuous time. So it's the signal is equal to time times drift plus sigma times Brownian motion, standard Brownian motion, which is basically like a random walk in continuous time. The size of the menu. I'll talk a little bit about this later, but not much. I mean, this is kind of the size of the menu is baked in here because, I have 2 dimensions and I've sort of collapsed them. I'm sort of, if I would have some sort of multi-dimensional stochastic process now. And so there are some models like that, but let's focus on this now. The model is silent. This DDM model is silent, and the world model is also silent.
If I can look at the sum,
Uh-huh.
depends on the fact that the cost is linear. Does it depend on normality, or that's philosophical other distributions?
It's
normalize some.
So it doesn't depend on normality, and it doesn't depend on the fact that cost is linear. It does depend on the IID assumption, though.
Yeah, I agree. So it's a constant bound of the sum.
Yes. Yeah, I am stating it in the normal version, Gaussian version of the model, because that's what corresponds to the DDM model. But the theorem is true more generally. I was hesitating. There is a formula, but I decided not to put it on the slide. So the book is by Shuryaev, Optimal Stopping Times, and he derives that formula. It's there. I maybe should have. I was hesitating, but I didn't. But in DDM there is no cost. And so let me just finish what DDM is, and then I'll get back to this point. So DDM, there's this continuous version of this cumulative signal, and the agent stops the first time the absolute value of this thing crosses the boundary and chooses left. If it's the upper boundary, chooses right if it's the lower boundary. Okay, and I'm going to write rho is distributed as DDM if it has this representation. So in the Wald model, if the state is SL, then rho has the DDM representation with drift D, variance sigma squared, and boundary B. And if this other state is true, then it's also DDM with the drift, the negative drift. And this model is silent about the cost. There's just some value of B, and there's no cost here. So it's just any actually B. That was a question? Yeah, we'll talk about that. We'll talk about that. Okay, so that's the DDM, and it's a workhorse. It has been a workhorse model of the cognitive literature because it's sort of easy to solve. So you can compute. If I give you delta, B, and sigma, I can compute the choice probabilities and the response times in closed form. So that's known in probability theory as the gambler's ruin problem. The first time the gambler run out of money. So the theorem is that if rho has a DDM representation, then the parameters are unique up to a common positive scalar multiple. So I can basically estimate them as an econometrician. And rho is a product measure, so the probability of given rho. So if I give you a probability distribution on actions and time, then
distribution comes only from one thing.
one triple or multiple of that triple. Yeah. Yes. Yep.
It's a one-to-one method.
Modulo that positive scalar multiple. Yeah. Yeah. The second point is that accuracy is constant over time. So these two, as I mentioned, these two effects counteract each other perfectly. And the third point is that actually we have kind of a softmax formula for choice probabilities. That's what's super tractable about it. And there's a formula for expected stopping time. There's actually no formula for the distribution of stopping times, but the expectation of it has a closed form.
So the second bullet means that your choice probabilities are the same regardless of when you stop.
Yes. And so, you can plot these functions. Yeah.
So there must be some reason why the second
I will get to that intuition. I will present that intuition in a little bit. So you can plot the choice probability as a function of delta. So oftentimes when people apply this DDM model, they think of delta as sort of the difficulty of the task. How close are the two items in their weight. And you can see that this is kind of a nice S-shaped function. And the expected time, So that's called the psychometric function. The expected time is called sometimes a chronometric function, and it has this hump shape. So the highest time is when drift is very small in its absolute value, and the bigger the drift, the quicker the agent makes the decision. That's kind of intuitive, right? If I have a very big drift, that thing is going to hit the boundary very, very quickly. Yeah?
Go back to the definition of the camera.
Yes.
Yeah, so there we have that T is L and T is larger than T. So it might be possible that the threshold T was crossed before, but then we go back into the middle and then it's not L. But
No, I think, sorry, this is just the way I wrote it. It's equivalent as if MT equals B.
yeah, okay.
You will never stop.
In the sense of,
Yeah, yeah.
it's reached and stay at.
We just stop, yeah. Mhm. Okay, very good. So we could be done. This could be it, right? We have some nice pictures. We have some nice formulas. Great. And people kind of were done for a while. They took this model and they really started running with it. But I want to convince you that there's some basic problems with this DDM model. And so the first problem is that, in the world model, there were two states. Either the drift is plus D or the drift is minus D. So this is a model that's well suited to situations like tasks, like character recognition tasks, where there are two characters, two states. And the Wald theorem said that's the optimal thing to do here. But now in these pictures we have a continuum of deltas. When people apply this model, delta, they apply it to tasks like the weight discrimination task. When there are two weights, they could be close in weight, they could be far away in weight. And so now we kind of have a model when there's a continuum of possible drifts. That gets back to your question. Continuum of drifts and continuum of states, not just two states. And no theorem says that DDM is the optimal thing to do for those problems. This is a different learning problem where the agent is learning not just about which item is heavier, but also how difficult the task is, what's the intensity of the stimulus, and that may matter for the stopping, right?
I wouldn't call this a problem with DDM. It's a problem with the misuse of DDM.
Sorry, yes, with the great.
It sounds as if
Okay, fine, yes.
DDM is a problem. DDM is no problem.
Okay,
It's
very good.
misusing it.
Perfect. Thank you, Sergio. That's absolutely correct. It's a problem with the misuse of DDM, overuse of DDM. The second problem is a problem with DDM in that it predicts, as we discussed, I haven't still told you why, but it predicts constant accuracy, whereas the stylized fact is that accuracy is decreasing in time. So that's a problem with DDM because even in character recognition tasks, accuracy is increasing in time. Sorry, it's decreasing in time, not constant. So there are various tweaks of DDM that have been proposed in these literatures to address this second problem. The first problem, I think, was not much of a concern, but the second problem was, because it's a basic fact that the model doesn't get. Mike?
I think we're pointing out when you say the stylized fact is that accuracy is decreasing, you're talking now about experiments where they're not just T. I think you're talking. I think the stylized fact is.
Okay, so it may also be a problem with the.
misuse.
So it's also a problem with overuse of DDM. Yes, sorry. Yes, good point. Thank you for the correction.
So meaning there are two choices. This stylized fact is not true.
Well, the empirical cases that I know of that I think that he's referring to as the stylized fact are all experiments where there are many more than two. Yes, and how many different random Gaussian
But that's not what you asked.
Yet you're asked, you have two responses that on different trials is stronger and weaker one. think there's noise.
So can I maybe?
That's an
So the random dot task is sort of isomorphic to the weight task. So the weight task is there's two items, one is heavier than the other, but there's a continuum of weights. There's a different experiment where there's dots randomly moving on the screen in some persistent direction, but there's also some randomness, so you can't exactly tell. And there's different amounts of randomness. And so that corresponds sort of intuitively to the weight difference. And so the random dot task is also a task where there's a continuum of states, and the intensity of the signal is something the agent is learning about. Okay, so people have proposed something that's called the full DDM model or extended DDM model, which is like a totally ad hoc model to me, where you random the sort of to given the drift and the boundary and sigma, you actually add some noise to the drift. So you randomize over the drift. And you randomize over the starting point of this cumulative signal. It doesn't start at 0, it starts at some random point. And you also randomize over the initial latency. So there's some non-response period over which randomize. And that could get you all sorts of things, but it doesn't seem to be like a principled model. So Drew?
Well, the simple thing of cost no longer being constant in time.
Well, yeah.
So
We'll get there.
For example, increasing in time probably is going to give you this immediately, no?
We'll get there.
It sounds like a simple correction.
Isn't there a way to rationalize, for example, a random drift? For example, in random dot experiments, that you would be attending to a subset of the panel, like a fragment of the panel, and so you would have some additional noise in how you evaluate the field.
Maybe. But the noise is already, I mean, there's already noise, given the drift, so.
That's right, but there would be more because you're subsampling.
In that particular task maybe, but in the weight task, it's harder for me to. Another kind of model is called accumulator models or race models in the psych literature, where each item has its own signal accumulation process and its own boundary. And you stop the first time you hit any of these boundaries, and you choose the item that corresponds to that boundary. Now that's a model that's been proposed as more sort of accurate in terms of how our brain is built. Maybe Rava will tell us why. I don't know much about that. But it's not clear a priori if this model is microfounded. And actually, I don't know anything like the Wald model that would give us this as an optimal thing to do. Maybe there is something. And the third thing is something that at least two people have already alluded to, is a time-dependent DDM model where the boundary is a function of time. And that's exactly the model that I want to talk about now. It is a model that actually does have a nice micro-foundation. And it has many micro-foundations, actually. So we'll see. So what is this time-dependent DDM? It is just like, we can just skip this slide maybe, and I'll just show you the picture. A boundary is a function of time. Okay, that's nothing more than that. So in this example, it's a decreasing function of time, and here on this path, the agent chooses right and thinks for 5.5 seconds, while on this path they choose left, and so on. Yeah.
Quick question about how to think about the experiment. So here you're thinking of one trial in isolation. So
Well, these are different trials.
I know, but the optimization problem is on a single trial.
Right now, there is no optimization
In
problem.
the optimization problem we talked about before, so the single trial.
No, it's no. It's across it's for maybe a batch of trials for which you have a fixed prior.
Okay, so my question is this, one way to do the experiment, which is the common way that you can do it, is you have, say, half an hour, and you're free to choose when you decide. Now, if you decide earlier for the first trial, that will give you more time to do more trials.
Mm-hmm.
And so there, the function to optimize doesn't have a linear time cost, but it's the reward per unit time. Now, my question is it equivalent or not?
I think so, because you know you in this remaining time you're going to solve more tasks. The more time you have, proportionally, you have more tasks to solve. So it's linear in time. It's not a proof, but it's strong intuition. Does that make sense? You don't seem to be convinced. What?
The problem though is there's some average amount of time.
I think you might be referring to the fact that the boundary will change not just a function of time, but also of history.
I think he's talking about the constant boundary.
That's why for each instance you are going to get a different picture, because the different as a function of the signals that you got, you adapt the boundary. That's something that depends on each experiment. You are going to get a different picture. You want a boundary where B is only a function of time, but not of the history. So that's already a little bit close.
By history, you mean how many problems I have solved and how?
History means the history of signals. Maybe the history of signals will determine how the boundary changes. In general problems, you could have that.
Surely, and that model does not have any byte. No byte. The model where boundary can depend on the history.
You can get any direction you want.
You can
there
get
are
any.
instances this way, instances that way. But in principle, that's the most general model.
That is the most general, and it's too general.
Yeah.
Yep.
I know.
Yep.
But no, I think that's what we wanted. That you have different pictures. I mean, for each time.
I think maybe you guys should talk about this because I'm not sure this is what he wanted.
No, but the question is, do you have an example where
We will not allow the boundary to depend on the history.
When there is correlation, when the signals are not any.
Okay, so before I talk about the, I said this model can be microfounded. I just want to make a simple point, but it's very useful for this kind of questions that I've highlighted as interesting. The boundary will determine accuracy. So the theorem says that if I have this DDM plus, the time-dependent DDM, accuracy is increasing if and only if the boundary is increasing. It's decreasing if the boundary is decreasing. It's constant if the boundary is constant. And so the intuition is that, if I have a decreasing boundary, then effectively, if I stop early, I must have cleared a higher bar than if I stop late. So I must have had more information or better information then, and so I make a better choice. And so that's also the intuition why in the world model or why in the DDM no plus, you get constant accuracy, because the bar, the threshold for choosing is the same at each point in time. So you have the same amount of information at each decision point, and so the quality of your decision is the same. Does that make sense?
For any IIT, you don't need DDM. Or is it really dependent on the...
So I think that's true. So I think in discrete time, I have a proof that it holds for any IID, but in continuous time, the only proof I have uses a Brownian bridge argument, and that works for Gaussian things. I think so too. I think so too. Yeah. So it's a pretty simple. It's not. This is not the proof. There is a little bit of a nuance there, because you have to. In this argument, you have to make sure that you haven't crossed the boundary already, and so there's some more checks that need to be done. Okay, so that's great. We have a model that can account for our stylized fact, but so far we have microfounded only a constant boundary. How can we derive another boundary? What's the optimization problem that gives us that? So here is one way to get there. It's a model that was developed by Chernoff, a statistician at Harvard in the 60s. It's very similar to the Wald model, except now we have a continuum of states. So I'm going to cast it as in the weight discrimination task. So there are two items, each of them has their own weight. And actually, this is not exactly the weight discrimination task. This is a task, this is a consumption task. So there are two items, sorry, I misspoke. There are two items, each of them has their own utility that is unknown to you. And when you choose the item, you get the utility of that item. So if I choose X, I get the utility as X. So S is the true utility, unknown to you, but you're learning about it, maybe from introspection, from memory. So that's the kind of model you would write for tasks where people are choosing between snack items. Lots of economists have recently run tasks like that.
The state is a vector of two coordinates, and you choose the coordinate, that's what you get. You're choosing
Yes.
the coordinate, and you're going to get that value of the coordinate.
Yes. Yes. There is a version of this for weight discrimination where we just have to tweak the utility function is now, you get 1 if Sx is bigger than Sy and 0 otherwise. It leads to a very similar model, but I'll briefly talk about it later. Now, each item gets a signal, an IID signal which is normally distributed with mean equal to the true utility and variance a constant, that's constant in time. And the prior over these utilities is also normal with mean mu and variance sigma 0. Again, it's sufficient to keep track of this cumulative signal, and that cumulative signal for each of these two items is a random walk with an unknown drift. These are sort of the formulas you've probably seen if you've dealt with normal models. The posterior mean, so the prior is normal, the signal is normal, so the posterior is also normal. The posterior is that the true utility is normally distributed with mean mu t and variance sigma t. Variance is a deterministic function of time. It's useful to think of it as precision. So the inverse variance is called precision, and it's a linear function of time. It's your precision, the precision of your posterior goes up linearly in time, and the posterior mean is a weighted sum of your prior and the cumulative signal, where the weights depend on sort of the noisiness, the signal to noise ratio. Okay. And so, without proving it, I'm going to state the theorem that says here the optimal thing to do is to stop the first time your posterior mean difference, the absolute value of the difference between the posterior utilities crosses a time-dependent boundary, a decreasing function. And if the prior is symmetric, then we can rewrite this as stopping the first time this cumulative difference in signals crosses a time-dependent boundary.
This is because of the continuum of states.
So it's not because of the continuum of
So what?
states. You could get that with 3 states. So you could intuitively, I think it's useful to get the intuition behind this by analyzing a task where there are 3 states. Either L is better R is better, and the third state is that you're indifferent.
So that's 3 points in R2.
Yeah,
One on the diagonal, one above and one below.
yeah.
That's
Yeah, and so let me get I'll get to the intuition in a second, and we'll see why this works. So, you know, in this Chernoff model, it's a DDM plus where the drift is equal to the utility difference. There's a square root here because I'm looking at the difference between two normals, so that you get that square root there. And there is some time-dependent boundary B.
You haven't said what the time dependence is yet.
I haven't, and so I told you that in the space of posterior mean, the K function is decreasing. I haven't asserted that it's decreasing in the space of cumulative signals because it's not always decreasing. It's eventually decreasing, but there are some parameter combinations for which initially it's actually increasing. And we don't know what the closed form is. This is sort of we know it's a function, you know, continuous Lipschitz or something like that, but there's really no hope for a closed form. We really tried.
For your previous story, we needed BT, not KT, to be decreasing in order to get an effect, right?
BT, yes.
You needed BT.
Yeah.
It's not the posterior mean that matters, but it's really the sum, the boundary on the sum.
Yes.
You can't get and indeed it could be that KT decreases and BT doesn't, and then you do not get the effect.
Yes, it could be. So
There are instances.
there are instances. There are not very many. You really have to force the model to, and I don't really understand why this happens. Something is going on. I mean, that's all I can say. Yeah, but mostly it's mostly decreasing for most of the parameter values. So I just want to explain a little bit the intuition behind all of this. So the main intuition for the Wald model is that this is a model that's time stationary. So suppose you observe, you know, that after a long time, these two signals are close to each other. But you know the drift in the Wald model cannot be zero. You're not indifferent between these two items. So this means this signal has no information for you. It's complete noise. And you throw it out and you start from scratch, basically. But what about the Chernoff model? In the Chernoff model, if you, after a long time, you learn that these two signals are close to each other, that's a lot of information for you. That means you're indifferent. When you're indifferent, you know, you should just stop and go home. There's no point in continuing there.
But there are two things going on in the Chernoff model. I mean, one possibility is that it might be indifferent, but it could also have been that you just have very noisy signals, as in the Wald model.
You could that's
But
not.
you're saying that the first effect was not in the Wald model, was enough to cause you to stop earlier than you would have had this been.
Yes. So if you have just the first effect, then you're time stationary, and so if you add the second effect, this stationary part is still there, but I also have this non-stationary part. So the sum is non-stationary, and so.
But then if the second result comes, the Chernoff case is because I care about big differences, but I don't care about small differences because of the form of the utility effect. That's hard to understand. And so if I cannot, then it doesn't matter to resolve small differences.
So there are two pieces of it. A, it doesn't matter to resolve small differences, but B, if the difference is small, then this is going to be a difficult problem for me. It's going to take a long time to actually pin down the true answer, and so maybe it's not worth it.
So the first part depends on the form of the utility, the second doesn't.
The
your
second
data.
doesn't. So the second part would also be true in the perception version of the
Right.
model, where the payoff is 0, 1.
So this churn out result depends on the form of utility or not? So for
It
one
does
reason-
depend on the form of utility, but I guess I'm arguing intuitively that if you wrote down a version, let's see, if you wrote down this perception version of the model, you would have the same, the second force would still be there, and it would be driving the result as well.
But you still gain a bit.
Yeah, but comparatively, there's a universe of choice tasks that I'll be facing, and some of them are easy, some of them are hard. If I learn that this is a difficult task, I have opportunity cost of time. I'm not going to spend time solving it.
So just what I was saying before about the reward per unit time,
Mm-hmm.
it's very similar to this. And I vaguely recollect that you found collapsing boundary for reward per unit time. That's why I thought it's not the same as linear cost, but I might be wrong. I might miss it.
Say that again. Reward per
So
unit of
here
time.
you're saying if I have a decision that I'm very unsure about
Mhm.
because I have inferred that
Mm-hmm.
the two options are closed,
Mm-hmm.
then I will not wait because
Yeah.
it's waste of time.
Yeah.
So that's the same kind of intuition for if you bound the duration of the entire experiment and you're allowed to do 1,000,000 trials if you want.
Yeah.
That's why I thought that setup would give you collapsing bound, and so was not equivalent to a linear cost. But I agree that on average, in my argument, that the average reward, and then there's a total duration of time, so it should be equivalent.
I think it is equivalent. It gives you collapsing bounds if you're learning about the difficulty of the task. If you're not, if you're just learning, if you're just character recognition with the same each task with same difficulty, you don't have collapsing bound, I think. Although this, I don't have a proof.
So basically we're learning something. We're learning two things at this point with the HC. We're learning, should I go, is the left item heavier or the right item heavier? And we're learning what's the difference.
Yes.
What's the
Yes, exactly.
Is there some assumption on the signals as to how the signals, how do I deduce about the signal? So now I'm deducing about two things. I'm deducing about output. Is there some, like I only care about these things. Is there some assumption on the signal that's crucial here?
I don't think so. Goes a little bit to Rava's question. I think you'd get the same thing with there's only 3 points, left, 0, and right. It's a little hard to prove it for me, but so here this is coming from the normal assumption.
And just to see if I have the equation right here, if if the weight difference is greater, I get a higher reward, my boundary will go down, and if as the weight difference between the two items is closer, I get a higher reward, my boundary on the system will go up.
Wait. The boundary is fixed, independent of the reward.
No, my decision boundary.
Yeah, the decision boundary is something you enter. It's a function of time, but it's a fixed function of time. It doesn't depend on the reward.
So you're saying in two situations where, suppose one, if there's an epsilon difference between the items, I get very high reward. If there's a very big, I get very little reward. And the other way around, if there's difference greater, I get a higher reward. If there's an epsilon difference, I get no reward. I get a very small reward. For those two situations, there would be no difference in the boundary.
I'm not sure I understand your question. So
I think he's asking about
Wald model.
change D.
Yes. Okay. If you change D, the boundary will change. Yes.
No, so I'm not talking about the wall model, I'm
Okay.
talking about Chernow.
Okay, but so change. Okay, so in the Chernow model, change the prior. So the boundary in the Chernow model will be a function of the parameters. So what are the parameters of the agent? It's sigma, the noisiness of the signal. It's sigma 0, the uncertainty of the prior, and also the prior mean, which is typically assumed to be symmetric, and what it actually is irrelevant because the agent only cares about the difference in utilities. And the C and the costs yeah.
So just suppose we have just three states
Mm-hmm.
with utilities 1, 0, 0, 0, 1, 0, 0, 0, 1.
Yep.
So there is always
Wait, 1, 0, 0. Wait,
the utility.
there are 3 items.
There are three choices. So three choices.
Three choices.
3 states. In each state, one of the choices
Aha.
is strictly optimal.
Aha.
Let's say even 1, 0, 0.
Good.
The utility
Okay. Yeah.
0,
Mhm.
1, 0, 0,
Okay.
0, 1.
Okay.
Will you get moving boundaries or you will get constant boundaries? Because that
Okay,
will tell us
so-
whether this fact of the indifference that you get on the diagonal between L and R matters or not.
But you don't have indifference in your
Exactly.
example.
So I want to know.
Okay.
That's
No,
exactly
so that's the class. That's the Arrow Blackwell Gershik paper, Econometrica 1959, and as far as I remember, the boundaries are constant in time.
good. So that really means that it's the fact that there are states where L and R are very close.
Yes.
That makes this
It's-
moving boundary.
It's the
That's-
fact
that's
that you're
the-
learning about
And not the
How
multiplicity of
much-
states.
yes. It's the fact that you're learning how much you care about the task, or what's the option value of waiting. Good. I'm glad you find it intuitive.
You had
Exposed to that.
you had a fixed cost.
I think interim. We're not exposed.
How does it fix cost? Some people have been trying to
How
do
much
it.
is worth to find more because of the excluded utilities? That's all there is to it.
Yeah, intuitively. Yeah, trying to prove this is a little bit of a pain. Okay, so you were just okay. Yeah, okay. Okay. Let's see, where were we? Anything else? So we were here. Yeah, so there's this other version. So that will give you a different boundary, right? Because we changed the utility function. So then you might ask, is any boundary optimal? Yes, if you now allow the cost function to be a function of time. So if you relax the time linearity assumption, for any boundary, I'll be able to find a cost function such that that boundary is optimal in the Chernow model. I think that's also true in the Wald model. I think that's also true in the Wald model. Yeah.
So far we are talking about choosing the optimal T, but can we also think about choosing B? Like
Well, these
effort in the intensive matter?
the optimal T and the B are they go hand in hand. If I increase the boundary, I'm going to wait longer.
No, sorry, not. I'm saying not the boundary, the parameter D of the drift.
So the parameter D of the drift is not something that you're choosing. That's part of your prior.
It's not something that you can choose. Like
The experimenter can choose that. So the experimenter can have one batch of the trials where the items are very close in weight, and another batch of the trials where they're wildly different. And they're going to induce a different prior in the agent, and we would expect different behaviors.
I'm thinking more about like a task or perception.
see. Yes. So yes. Okay. I see what you mean. So okay. So it's like a model where you sort of can endogenously pay more attention. You could have a model like that. We talk about it a little bit in the paper. I decided to opt. I'm gonna leave all the attention stuff to Lumi and others. But just before I take the next question, there is an element of attention here because the longer I wait, the more signals I get. So it's like paying more attention, and in fact, there's also a cost of attention. You know, the longer I wait, the more costly this will be. But you were talking about sort of within each instant, I could also optimize attention. So that's different.
I have worked in some papers where I incentivize them to pay more attention,
Mm-hmm.
and they do better, but I don't see difference in time. They just do better.
I see. That's interesting. So that's not what this model would predict. This model would predict shorter response times if they pay more attention. Yeah. Yes. So Rava asks. So there's actually a formula in the Wald model, how B depends on D and sigma. Not D. Yeah, D and sigma and the cost and C. In the Chernoff model, there's no formula, but there are comparative statics. In our paper, there's a proposition that talks about it. Yep.
There are some economic intuition behind that because I thought that one should just use without like a generality equal one because otherwise you just blow it up linearly the exponential mod.
Yeah. So these are all unique up to. You can normalize D to 1, but then you can't choose D and sigma. Mhm. Okay. So one, and actually, so on this, there are actually papers in cognitive science that talk about, that take this more seriously in that they try to estimate the nonlinear cost function from the data. So one last thing that I want to talk about is do difficult choices take more time? So we've sort of seen this kind of hump-shaped function in Mike's lectures, and also, you know, we got it from the DDM. Harder choices that the way it's implemented is the absolute value of delta is smaller, and because the what's called the chronometric function is hump shaped around 0, that means harder tasks will take more time. This is also true in with collapsing boundaries, harder to show. But what's the intuition? This is a little bit confusing to some people, maybe not you, but some people that shall remain incognito in the behavioral economics crowd are confused about this question because it is somewhat confusing. Because if this is a difficult choice task, you shouldn't spend more time on it. You should just toss a coin and move on. You should spend time on easy decisions. The twist here is that you don't know as you go along. You don't know whether the task is difficult or not. That's something you learn about, but you start with your prior, so you don't know that these two signals were close to each other. That's something you learn after a long period of time. Okay, this is my last slide, so I'm happy to stop here, take more questions, have early lunch.
So increasing the probability of difference of the states where left and right are the same, you'll see that by playing with that.
Oh yeah, if you manipulate the prior, then you will. Yes, yes. Yeah. Yeah. Yeah, so there are some, maybe should have talked about, there's some versions of the DDM model where it's not a diffusion, but it's a sort of autoregressive process, Ornstein-Uhlenbeck or something like that. I don't know much about these models, and I don't know, these are sort of, I don't know what's the micro foundation for the model, what kind of boundaries. I would imagine now the boundary will be a function of the history in those models. So I don't have much to say. Yeah. Yeah, I suppose with non-IID models, you would get that, but with IID models, this surprise plays no role. Yeah.
Another extension to figure out the optimal stopping time, one would want to have an estimate of what would be the expected gain if I were to continue.
Yeah.
However, with boundaries, these are fixed in time. These are fixed functions of time. It seems like that problem has been kind of ignored altogether, and then the boundary has just been given, and now I have.
Well, the boundary reflects that calculation. The speed at which the boundary is going down in time reflects the fact that, as you go along in time, you're expecting to learn less.
Yes, but this boundary doesn't fit to experimental data.
Okay, but in the turn-off model, the boundary is optimally chosen by the agent to reflect precisely those kinds of effects you were talking about.
Yeah, but that already presupposes the functional form of the, when we perform the Bayesian.
Yeah.
It already presupposes
Yeah.
the functional form of the noise.
Yes.
That
I mean, you got to start somewhere. If it, yeah. Yes. Not that I know of. These kind of things live in a very different space, because this is choice between alternatives, not the kind of tasks you were referring to as just stating a degree of belief. I mean, in principle, one could try to apply a DDM to something like that, but I haven't thought of this. Yeah.
to add on to her question, I'm more concerned about self-learning phenomena where an experiment I recently asked of this A versus B, under these models, if they are really, really close, then there will be some chances that are some chances it will answer A, some chances answer B. But I think, like in the self-learning phenomenon, the subject would stick with their first choice. They would remember that they made that choice before, and it would reply with the same answer. So would that more would you add to that model to account for that, or?
So I suppose we could add this to the model, but the empirical regularity is that people do not stick with their answer. People choose stochastically.
And the important is the experiments you're talking about that they don't know that it's the same schedule. They gave an age.
Yes.
They don't have any way of
Yes.
deciding to stick to
Yes.
the
Yes. But in the right, But in the choice in between lotteries, they kind of see it's the same lottery. I mean, maybe they haven't
But it's the idea is that
imperfect.
they don't
Yeah,
remember-
right, right.
they
No,
don't
no, but
remember what they
yes,
said
yeah,
about it
yeah,
before.
yeah, yeah. There was a question there. Yeah.
In experiments where you use time pressure and persistence of the object so that they exhibit more errors, how will the time and cost model account for that?
So I think even the Wald model could account for that, the DDM. So if you time pressure, you could imagine being a higher cost. And so higher cost is going to mean lower boundary, and lower boundary means faster and worse decisions. Does that make sense? Yeah.
Then again, another short question then. There are these experiments where you have sequential multiple tasks, and some of them, especially arithmetic tasks like multiplication and addition tasks, these people consider them like attention sets. They're timed, so they give you, let's say, 5 seconds to do a simple addition task, and then the next task is a harder task, and then the time limit is 2 minutes, but most participants receive the data, they do response time, an average of 1 minute, for example. So when you have this, I'm trying to think in terms, and I see that in many experiments. So in that context, how we can think of, because the data so far show that when the task is timed, people mess up. Like when they have 5 seconds to do something about the stress, the timer, and then when they have more time, response time, despite being intelligent, sometimes have no effect. They do the same thing, but then it's not associated with making better decisions. So how you would guide this type of realistic model?
I don't know. I think it's sort of a paradox in the if you put yourself in the shoes of this model, this should not happen. So I don't know what to do. Probably need a different model. There was a question somewhere there. I know. Okay, Sergio. Yeah, but I don't see any hands up. So you get the last question.
The Chernoff model, this what's called M bar T is not the only sufficient statistic, right? For example, what we call mu T is also sufficient statistic. Or I got it wrong.
Sure. I mean, there can be many sufficient statistics, right?
Okay. So the point is, but your result was that in order to get an increasing accuracy,
Mm-hmm.
increasing accuracy,
Yeah.
whatever, that really depends on MT as a sufficient statistic. Why I find this a bit surprising. Why? I mean, because somehow the problem doesn't have a built-in that the M bar T is the one you should look at. I could look at the mu T, for example, and I should get a parallel result of that.
I think you can. I think you can rewrite this because, M and mu are. There's a one-to-one relationship between them. You can
this theorem, if I put instead of b mu, the theorem is no longer correct.
No, then you're gonna put a k here. As the
I mean, the
function
boundary
k.
of, sorry, the boundary of mu, I mean.
The boundary of mu, but a transformation of that boundary will have to be decreasing or increasing or constant.
I see. Whereas for m, it's just a straight.
It's just the pure boundary. That's why I presented it this way, and also because the people who use DDM, they just look at M. They don't have a mu because they don't care about the optimization problem of the agent or their beliefs. They just care about sort of what they call the signal, cumulative signal. So that's more informative for the DDM people. I want to say DDM people. That doesn't sound good. Eric?
If there are no further questions on this lecture, I was wondering if I could go back to
Absolutely, yeah.
the first one. You said something that almost in passing I didn't quite follow. You said that there are, you were talking about justifying Bayesian updating in these models, despite the fact that we know that there instead of asking people what do you think the probability of this is, that put them in an experimental setting where they were over and over having to react, take some decision,
Right.
that they would be more likely to update probabilities correctly.
I don't think so. I'm not an expert in this literature, but I think there are versions of these experiments run with sort of savage acts, where each action corresponds to a belief, and choosing these action means you have that kind of a belief. And you still see these kinds of paradoxes. So it was more about sort of explicitly reasoning about the states and the beliefs versus having them this Bayesian updating baked into your response function. And no, this may not mean anything, but this distinction may not be very meaningful.
So I'm not clear on when Bayesian updating is okay and when it's not.
I think if you had clarity on that would be fantastic. But I don't think anybody has clarity on when it's okay and when it's not. Yeah. Okay. Thanks a lot. I'll be here for the next 10 days, so hit me up.